Hello, and thank you for your interest in Alfing Corporation's AMT product group. Alfing Montage Technique, or AMT, is a world-class manufacturer of advanced tightening, automation, and error-proofing solutions, specifically designed for today's assembly industry. We provide several unique solutions, many of which have never been introduced to North America before. The first solution that we would like to introduce to you now is called our guided cell solution. This unique solution includes all the controls, software, and hardware required to complete even some of the most complex assembly processes without production errors. Even the most inexperienced operators can successfully complete complex assembly processes without error with our on-the-fly guidance and auditing capabilities. The guided cell solution can be set up to be used with simple production screens, or it can be set up to include complete work instructions, including easy-to-follow pictures and diagrams. Detailed process coordinates and immediate QC feedback and results auditing are communicated to the operator in real time. Tools and other peripheral devices can be enabled and disabled based upon these results. This technology could virtually eliminate the need for costly, redundant production line auditing that so many companies utilize now. So what we'll show you now is a little more detail about our guided cell solution. This one solution has the potential to build, say, for example, several different vehicles all with the same equipment. In this presentation, we'll show you, for example, how to build two different vehicles. Car A, which is our yellow car, Car B, which is our green car. Let's build Car A first. All we need to do is get the identifier for Car A into our controller, let the controller know which car we're building. That can be brought in via a digital input in many different ways. In this case, we'll do a barcode read. So when I barcode this yellow car here, the system now knows that I'm building Car A, and it has the ability to step the operator through every step of the sequence in the build process and do immediate quality analysis of the results, as well as storing the results to this serial number or VIN number. So the first thing we need to do is choose cable tool number 1 and socket position 1, in this case 104 in our socket tray. Socket position 1 is also lit up. If I pull the on socket out, it will not give me a release. None of these tools will work until the operator does exactly what we're asking them to do, which is socket position 1 and cable tool number 1. Even if the operator comes over here and grabs a battery tool, for example, all these tools are disabled. The only tool that's enabled is the one we're instructing them to take, which is cable tool 1 and socket position 1. You notice when I took socket position 1 out, we now have a tightening point identified. The tool now has a release on it. So we're able to do one tightening to 13 Newton meters. After I tighten this to 13 Newton meters, I'm going to keep my hand on the trigger, which will keep my display up, and we can talk about a couple important items. Okay, so after I do the tightening, it evaluates, it says, was it good or bad? We got a green light, which means it was good. And when I let go of the trigger, it will release to the next step. Okay, so the next step in this case now is not this cable tool anymore. You can see we're running battery tool number 4 to 10 Newton meters. We can basically put whatever information you want to show your operator on the screen. I'm purposely not going to put socket position number 1 back where it belongs just to make another point in just a minute. I'll leave it right there. But right now I will come over here to my tool choices. You can see I have a lot of tools. I need battery tool 4. It's the only tool with a blue light, and again, it's the only tool that will actually operate right now. You can see on the screen we need to run 3 tightenings. Tightening 1 is good. We get a green light and a release. Now I set the programs up in here specifically for tightening joint A. I'm going to show you what will happen if I try to tighten on tightening joint B, which has slightly different unique characteristics to it. So now I'm going to go to B, and the system is actually smart enough to identify, even though those bolts are exactly the same, there's minute differences in the characteristics, and we can get a red light. In the case of a red light, when we're setting up the programs with our customer, we say, how do you want to react to a bad rundown? Perhaps you're going to say, I don't want any production done at all on it. I want the automatic conveyor to shuttle this vehicle off to a rework area, or maybe you're going to say, let's let the operator try to loosen it first and try to tighten it one more time, or 2 more times, or 3 more times. It's all just programming. So we can back it out now, and that's the only way this tool would have ran. If I tried to go forward, it would be disabled. When we get a good back out, now when I put the tool in forward, it will work. And we're giving the operator another try to have a good rundown. They succeeded. Now we can go to the third tightening, and if all 3 good, we go to the next test plan, which is the next event in the sequence, which now is back to our cable tool number 1, but we need to pick socket position number 3. Now please watch closely. I have number 3 lit up. I'm going to pull 3 out, but I didn't get a release. And if you remember earlier in this video, I said I was going to put socket number 1 not back in its correct place, right? Only when I put it back will I get the release, but it's even smarter than that. If I take socket that's supposed to go in position number 1 and I try to put it in 3, it won't fit. There's no way to have, with our solution, the wrong socket in the wrong position, which is critical. So I'll put socket 1 back in the correct position. I get a release to the tool. I can see that in this application I have 2 tightenings to do, which I'll do now. 1 and 2. We move on to the next step. The next step here is actually called a subassembly error-proof step, if you will. If I'm building 10 different vehicles here, 10 different boats here, whatever I'm building, it's typically understood we're probably going to have many different subassemblies we could choose from. Each of the subassemblies has one vehicle it's really designed for. So for example, if I grab a subassembly for car B, which is the green car here, and I'm trying to build car A, I'll show you what will happen. I'll scan a subassembly for the wrong car, and because this system is so intuitive, it actually says, you grabbed the wrong subassembly. You got an error. You picked the subassembly for car B. I now lock the tool up, and basically I'm telling the operator, put this subassembly back and get the right one. So now when, on my second try, I scan the correct subassembly, then and only then do I get a release, and we move on to the next step. This step is called a manual operator. This actually came about because not long ago a customer says, John, I love all of your error-proofing capabilities with your tools, but I have other problems too. For example, the operator forgets to put a hose clamp on, or they forget to duct tape something, or what have you. This basically asks the operator to acknowledge that they did something. It's just a reminder. So they push the acknowledge button. Yes, I did do that. Now we can move on to the next step, which is another unique solution from AMT. It's called a digital torque wrench. The digital torque wrench is wirelessly communicating with our controller. This one torque wrench could do 100 different jobs and is instructed which job to do, again, based upon the vehicle or the part that we're building. So we need to do 2 tightenings here. I'd like you to notice, if you would, on the screen that not only are we going to tighten to torque, but we have the ability of also including angle monitoring, which is very important. And you'll notice here that when I hit the correct torque, I get a green light. You can see that I have a torque of 5.5 newton meters and an angle of 40 degrees past threshold. That same information is displayed on the face of the digital torque wrench. So if we get 1 green, we can go to the next step. Nice thing, it's a ratcheting head too, so we're able to repeat. And we have 2 good rundowns. We're done with the wrench. Now we will go to our battery-operated pistol grip tool, which is also wirelessly communicating with our controller. If you remember the last time I did this tightening joint, I tightened it, right? And typically we don't want to re-hit a joint. So I'll show you that if the program was wrote correctly, we can identify that and give the operator a red light and disable the tool. And it was written correctly because we did get a red light. Now we have to back the fastener out and try again. Okay, so we fixed it, we repaired it. Second try, green light, life is good. And now you see an overall green, which means car A, the yellow car, was built correct from start to finish. All of that data is going to be coded to car A via the model number and serial number and permanently stored in our controller and back to the customer's network if that's what they want to do. All right, so now we're going to build a completely different vehicle, car B, the green car, using the same equipment, completely different work instructions, completely different tightening parameters, and tying the data to a completely different vehicle. So again, we need to capture the information that identifies car B. We can do it with a barcode, or we can do it with a digital input via the customer's server. So we'll do a barcode for car B. System says, yes, we have car B, but we need to use cable tool number 1, which is right here, and we need to use socket position 2 this time. When we pull socket 2 out, we're ready to do 2 tightenings. Tightening 1, and you can see here we hit 10 newton meters and 165 degrees past our threshold. Now we're ready for the second tightening. It's good. We move to the next test plan. I'll deliberately leave the socket in the tool again to show you how the error is captured. And tool 4 is the only tool that's enabled. We need to do 3 tightenings. 1, 2, but now I'm going to jump onto the wrong bolt. I'm supposed to use bolt A. And you can see that actually is smart enough to know that I'm on the wrong bolt. Give me a red light and shut all the tools off until I make a correction. The program is set up to let the operator back it out and try again, I believe up to 3 times. Okay, the sequence is complete for this test plan. Go to the next step, which is the correct subassembly. Boom, we know what we're putting in. We're putting it into car B. It's analyzed and it's passed. Digital torque wrench, 2 tightenings here. It's good. Same numbers show up on my display as do on my controller, which was 4.3 newton meters and 93 degrees of angle. Second tightening is passed. Now we're going to go to another very unique tool. It's actually a battery operated, wirelessly controlled rivet tool. It's unique in that not only do we not have an air hose or a cable, but also we're going to do a batch count of 2, but verify that the 2 that we do are actually correct based upon force and distance monitoring. So we have 2 rivets to pull. Rivet A is popped and analyzed, and it was correct. You can see here that we have a force of 18.08 and a length of 17.42 millimeters. So I have 1 more rivet to pull. Pop rivet number 2. Verify that it was good and pass it if it is. Manual operator, did I do something? In this case, have you mounted the hose? We can hit OK. Get an overall green. So now we've successfully built 2 vehicles here, all with the same tools, completely different work instructions, and error proofed.